Alright, this is, oh, this is Blue Book Chapter 6. The first thing in 6A is called measurement, and the first thing they, one second, okay. The first thing in here is called measurement, and it's about circles. And you may already know about these two formulas related to circles. In this formula, R is for radius, and the radius is the distance from the center of the figure to the figure itself. So in this case, the circle is only, here I'm going to make it a different color. Whoops. Oh my gosh. Make a different color. Red. The circle is only this red part. It is not the white part. You can think of the circle as being, including the white part, like the circle is a plate, and you can put, items on the plate, or whatever. I don't know what these are. You can put like a chip, put chips on the plate, but that's not what's going on here. The circle is simply the red part. And so we have the center of the circle, we have the circle itself, and then this distance is r is the radius. So the unique feature of a circle is that the radius is the same from the center to any point on the figure, and just sort of by contrast, you could have this kind of figure is called an ellipse. And it does have a center, but the radius here is not the same as the radius there. So this doesn't have a radius. You could take the radius anywhere, or you could think of a polygon. Here's a hexagon. You could take the radius there or there or there. So radius is just this. It's a Greek root, radial, or radio, or radiation. These are all the same thing. Okay, I'm talking a lot, but I don't know. It's been a long time since I made one of these, so I don't remember how to do it. All right. So yes, if you want to know the circumference is if you were here and then you ran all the way around the circle, how far would it go? The area of the circle is there, and the area is just the size of the plate, or like if you wanted to cover the plate in something, how much would it require, that kind of thing. So that's the difference between area and perimeter. The area formula is, the circumference formula 2 pi r, or it's like this. And if you read it out loud, it rhymes. This is not good handwriting. I'll work on that. And then here's the star. Oh, it's not very good. The area formula is different. Area. So r is still the radius. The radius is the only number you need to use to describe the size of a circle. The location of the circle is a different story, but all you need is one number r. So that goes like this. Why is this handwriting so bad? And so here's the bear. Oh my gosh. Okay. What they're developing in this section is part of the circle, so a sector. A sector has an area here and an arc is only, again, part of the circle and not the entire circle. So I guess in terms of how I was talking about circle before, the arc is a part of the circle itself, and a sector is part of like that plate version, or like a pizza. If you cut a piece of pizza looks like this, um, in math terms we would call that a sector of pizza, and the sector has a size. I think, like for pizza, the arc length is like the crust, and then the sector is the pizza itself. I don't know why this handwriting is so bad. I'm just going to keep working on it, so hopefully it gets better. Alright. Oh, I lost some of the rhyme here. I'm not using the normal recording thing that I used to use, so I don't have a strong idea of where the screen region is, but whatever. Okay, so there's not very much going on in this. The section's pretty short. In either case, if you want to find the length of part of the circle or the size, the area of part of the circle, what you do is you think of it like theta is the angle. Okay, theta is a Greek letter, and often you will see Greek letters used for angles because we're already using x. Oh, we're already using x and y for x and y values in an ordered pair. And so theta and x and y can all be necessary in a single problem. And that's why you will often see Greek letters used for Greek letters used for angles. So if you want to know the length of an arc, first this is arc. First you determine how much of the circle does the arc use, or how much of the circle does the arc include. That is the angle that describes the arc, right? The arc starts here and ends here, so the angle is the size of it. And there are 360 degrees in a circle. So this is like the percent of the circle. So if theta is 10, we have 10 over 360. Or maybe we could say the fraction of the circle. It's not necessarily a percent. Fraction of circle. So theta is whatever it is. Let's say theta was 10. 10 over 360 would be 1 over 36, I guess. So you'd have 1/36 of the circle. And then you multiply this by the total circumference of the circle. So this is an arc length formula. If you know the number of degrees and the radius, you can figure out how long the arc is. Very similarly for the sector area. For the sector area, you start again with angle size over 360, which is the fraction of the circle, and then multiply it by the total area, pi r squared. So this is sector area. And then the problems in this section, I'm going to pause this and then put some problems here, hang on. Alright, the problems in this section are pretty much like this. It's summer vacation, and I think I told you all I'm not giving you summer work, so you can decide if you want to do this. Is still section 6A. So like in your blue book, this is on some page. Hang on. Page 133. So if you want to do problems from this. Okay, I'll show this one though. This is example 1, I think. 3 significant figures, so we'll need a calculator instead of leaving it with pi. Actually, I'll tell you what. Well, I'm probably going to leave it as a fraction because I don't want to take the time to get a calculator out here. So you'll have to calculate it if you want to match the answer in the back or the answer that's given in the example they show you on. So for part A, the length of the arc, in this case theta is 48 degrees. Here's theta. And then so our formula is what part of the circle do we have? And then times the total circumference 2 pi r. So in this case we have 48 over 360 times 2 times pi times the radius, and the radius is 3. So, well, so I could just write 3. And this is a perfectly, I mean, this is an answer to the problem. It doesn't go to 3 significant figures, but this is called an exact answer. It's not very simple though, and there are some obvious ways to simplify this, so we will. 48 over 360, I think we can divide those both by 24, maybe? I think 24. So 24, here, let's see. Well, I don't know, 48 divided by 24 is 2, that's not too bad. 360 divided by 24 is not as easy. I'm just going to do this. I'm pretty sure 24 goes in, but I don't know. Yeah. Okay. So 2/15 times 2 times pi times 3, so that would be actually, I'm going to leave the 2 and the pi and the 3 separate because I can do something with this. Now notice that this 2 and this 2 look like you can cancel them, but this is 2 over 1. This is 3 over 1, and I guess pi over 1. So 2 and 2 are both in the numerator. 3 and 15 are numerator and denominator here. So I can actually simplify those. So I have 2 over 5, 3/15, that would be 1. I can divide them both by 3. Times this 2 times pi, or we could say 4/5 pi. So when you go to, put your answer in the calculator, you can type this, then you should get their same answer from the book, and it should be right there on page 133 if you want to look. Alright, I'm deleting this, but you can just reverse the video if you want to see it again. Perimeter of the sector, I am again going to keep it exact. We had 4/5 pi from before, that's this. And if we want the perimeter, we need this part and this part also. So each of these is 3, so this means it's plus 3 plus 3. I'm being super thorough. So this would be 4/5, oh my gosh, pi plus 6 centimeters. Alright, the previous answer was also centimeters, I just forgot to write it. For part C, and again, you can calculate that if you want. Oh gosh, this has been 14 minutes. This is what happens. Alright, for part C, the area of the sector, we have 48 out of 360 possible degrees here, right? So this is the fraction of the circle, which I think I decided earlier that this was 2/15, right? Yeah, it's 2/15. Yeah. So that's 2/15 times pi times r squared. And r is still 3, so 2/15 times pi times 3 times, okay, I mean that's kind of artificial, times 3 squared is 9, so this is 9. So you could leave it like this, you could put like 18/15 pi, but I would almost always say you should simplify something like that. We can divide them both by 3, so we get 6/5 pi, and the units this time are centimeters squared. So other problems in this section are basically the same kind of thing as this. I'm going to pause and look and see if there are any interesting ones, but I guess we'll see. Alright, I'm back. I think this one's interesting because of the shape. Like, finding the area of a shape like that is not something you would have necessarily done before, so we're going to do that. Alright, x and y are the centers of the circles containing the two arcs. So x is the center of this circle out here in pink. Here, I'll make it better. The pink circle has the center x, and the green circle has the center y. Alright, and then they both kind of meet at these 2 points A and B, and there's a moon shape there. So I think that's kind of neat. That's why I'm doing this one. If you don't want to see this one, then just, stop watching the video here, I suppose. Alright. So the length AX. The length AX, because this is a right triangle and we have 16, and the points A and B are both on the same circle. This is also 16. It's the radius of that circle Y is 16, and so we have 16 and 16. And then this is the third side of a right triangle. Now, we will talk about special right triangles later in this, I guess, series of videos. But for now, I'm just going to tell you this is 16, this is 16, this one is 16 times the square root of 2, and so the length AX is half of that, and so AX is 8 times the square root of 2. The perimeter of the shaded crescent. Oh, this is part B, and this is millimeters. Okay. The perimeter of the shaded crescent means we have to add these two arc lengths, which I drew earlier, and then I guess I got rid of them. So we have red here and green here, and we're going to draw these. We're going to find these two arc lengths and then add them. So for the red one, we'll just do it in red. For the red one, we have let's see. Oh, here's another. Well, I guess since this is marked as 90, we can say 90 here. That's a little bit. Okay. Okay, so listen, the red one is here. Okay, never mind. So the red one, we have 90 degrees, and we have this much, so 90 over 360, which is 1/4, right? And then so 1/4 times pi, 2 pi r. And we know r is 16, so 1/4 times 2 pi times 16. 16 divided by 4 is 4, so I'm going to make this 4 times 2 pi, so this is 8 pi. Okay, that's the red length. For the green one, they're telling us that, I don't know if there's, it feels like an assumption. I think we can assume that x is the center of this circle, and so if this line segment includes the center, that makes it a diameter, and so this angle here is 180 degrees, which, okay, so look, actually here, I'll tell you what, I messed this one up because I'm having a hard time separating these two circles. So the red arc has this red center. This, you may have picked up on this while I was doing the problem and wondering what was going on. So that's 180 over 360. This is not 1/4, this is 1/2. Just do this part again. Which actually, if it's twice as big, then that really does just mean 16 pi, but let's do it anyway. 1/2 times 2 times pi times 16. This time I'm going to do 1/2 times 2 is 1. So here's our 16 pi millimeters. Sorry about that. The green one is the one that has this angle, this green angle. I'm sorry, the green angle is 90 degrees in size, and so we've got that, and the radius is still 16. Oh my gosh. Okay. I am going to delete. Okay, I messed this up again. Let's go backwards a little bit. I was just not thinking when I was doing this. I got. Okay, here's the mistake I made. These two circles in red and green don't have the same radius. And like I say, you may have already noticed my error from before, so sorry about that if you've been trying to follow my explanation. Okay, let's do the red one first. The red one has the center here. The angle is 180, and the radius is this distance AX here. This is the red radius. So our size of the angle, we have 180 over 360, which is 1/2. So 1/2 times 2 times pi times 8 radical 2. Now 1/2 times 2 is 1, so we have 8 pi times the square root of 2. This is the red arc length. The green one has the center here and the radius 16 is the green radius. This angle is marked as a right angle, so we have 90 over 360, which is 1/4 times 2 times pi times r. Oops, r is 16. So 1/4 times 16 is 4, and so I am going to make this 2 pi times 4, and then this is 8 pi millimeters. This is also millimeters. So our total perimeter of the shaded crescent would be 8 pi times the square root of 2 plus 8 pi. Now, they very obviously have 8 pi as the greatest common factor, so I think you would often see the answer like this. This is millimeters. Now, I think they are making you, I think they make you use a calculator to get 3 significant figures, but whatever. Alright, so I'm getting rid of this. Alright, I'm trying to go faster for this last part. The area. The area we have still... Okay, we still have the two sectors, and I think we can just subtract the small sector from the big sector, because actually no, both sectors don't include this triangle, right? Alright, so what we want to do, there are 3 regions here. We have region 1 is the one we want, region 2 is this little sliver, and region 3 is this triangle. So if we find the area of the green sector, okay, that would be region 2 plus region 3. Okay, what we want is just the size of region 2. So finding the area of this combination, find the area, the combined area is just the sector area formula. And so that is, the green one has the central angle of 90, so 90 over 360 times pi times 16 squared. So I'm just going to leave it here for now because I don't know. I guess that's 1/4. Actually, this is not too bad to simplify. 1/4 times pi times 16 times 16. This is 4. So I have 4 times 16 is 64, so 64 pi. Okay, this is the combined area of region 2 and region 3. If I just want the area of region 2, then the reason for that is that region 2 is also like region 1 plus region 2 is this red sector, which is I guess half the circle. We don't really have to be elaborate about that. So basically what I want is to do the combined area of 1 and 2 minus 2, but in order to find 2 I have to do the combined area of 2 and 3 and then subtract 3, which is easy to get because it's a triangle. So I'm going to do the triangle one in blue. Here's our triangle. Triangle area is 1/2 times base times height, and the base and height are both 16, so we have 1/2 times 16 times 16, so this is 8, and then 8 times 16 is 128. Okay, so the size of region 2 is, which one's bigger? 64 pi minus 128. And then this is millimeters squared. Okay, that's not finished though. What we need to do now is find the area of this red semicircle and then subtract that from it. So the red semicircle area is red sector. Red sector is 180 over 360 times pi times r squared. Now r in this case was 8 times the square root of 2 squared. So we have 180 over 360 is 1/2 times pi times 8 times the square root of 2. So I'm going to make it 8 squared times, oh my gosh, look at that. Look at that 2. 8 squared times 2. I got the 2 by squaring this part. And I'm doing that because these two will cancel out. So this is 64 pi. Oh, interesting. So the combined area of region 1 and region 2 is 64 pi. The combined area of region 2, I'm sorry, just the area of region 2 is 64 pi minus 128. So this is weird. So what do we have? 64 pi minus 64 pi minus 128. So this is just 128. It's interesting that they made it that way. I'm just going to check in the book. Let's find out. Yeah, it turns out that's right. So this was a 30-minute video. I'm not going to make them all 30 minutes, so sorry about that. Anyway, that's the end of that's all I'm going to say about Blue Book 6a.